Hello, everyone. My name is Enrique Ramírez. I'm a software engineer at Tesco, and today I'm going to talk about hardware development with KMP and a little bit of Compose multi-platform. So let's start. Yeah, but first I want to introduce the topic. First, talking about a passion of mine, which is guitar, all the guitar world, and specifically like guitar pedals. So, what is a guitar pedal or a guitar pedal effect? It's just something that takes an input signal, the one of the guitar, and it transforms it into a different signal. To bring this to the software world, let's imagine this like a guitar input stream. So the guitar is your stream, and you can see each effect as a mapping function, and you could change in different ones. Let's say we have a compressor, phaser, an overdrive, equalizer, delay, different kinds of effects. And these guitar players really like pedals. Like this is, imagine, think of it like the same thing we do, the software engineers, with our setup. The more screens you have, the better, that kind of thing. Like, look, how's my setup? Well, guitar players are kind of the same with pedals, and they also like to collecting them. The more, the merrier, kind of. And with different pedals, what you do is you combine them to create different sounds. And when you get the different sounds, you can use them in different parts of the songs or on different songs. But this brings a problem. The problem is you need to switch many pedals. Many buttons at the same time. You are on a section of a song, like going very heavy with it, and then the next section is quite like a different sound. It's clean sound, has a different set of effects. You need to do a lot of pushing and a lot of clicking very, very quick. So I was thinking on we could solve this by developing something. So there's a component here that is the switcher. We can connect everything to the switcher, and somehow we can talk to it with some sort of computer and then program it. So every time we click on a button, we have the different set of pedals. And so it's just one button, one sound. Just another button and another sound. So that's where the project, I call Matrix 8, starts. So what do we want? We want to be able to switch multiple guitar pedals instantly. Click a button, all of them, they rearrange they rearrange and you enable the ones you want. You want to see it. We want to know which ones are selected. And also, it will be good to have a companion app for doing the editing of those effects, so you are not editing there and during the gig, but you have something you can edit with. So just playing a bit what is a switcher. Just a very basic example here, just a pedal board with 3 pedals, the simplest one, and this is a switcher that is a 4x4. It just creates paths of where the sound goes, right? So we want to connect, in this case, the guitar to the pedal 1, and then from the pedal 1 input, then from pedal 1 output to the pedal 3 input, and then to the amplifier, so we can hear the sound and how does it look like. So that's and the switcher will do will create the path for that. That's basically what the switcher does. And yeah, I was searching online, what are those switches? How do they look like? I found chips, the data sheet of this chip. And it says it's an 8x8 switcher, switch array. And it communicates with something called I2C. I don't know what that is. Let's see. Let's carry on. Let's remember that for later. So you take that chip, and then you do your schematics, and then you get into a bit of circuit creation. You get your PCBs, You get them manufactured, and then you might get the service that they build up for you, or you build it yourself. Soldering the components, and then you get that chip home, and then that's kind of the result that you get. That's that chip that I found. I created the board, and now I have it, right? But and that will be the one for the where you connect the pedals, the jacks. And also, I had a little bit of 3D printing, just so it's not a mess on the left side. We can see how the first part of the project was with all the cable mess, and then with 3D printing, keeps everything super clean and tidy. But how do we build this, right? How that we have the circuit, but how do we talk to that, right? And we are mobile engineers. We're not embedded. So how did we do it? I don't know if you watched this film, like The Karate Kid. But basically, the main character is given a lot of chores that in the beginning they have nothing to do with karate, and he's frustrated. But then at the end, it turned out that they were useful for defending. So lots of things like wax on, wax off, and they turn out to be useful. And those are transferable skills. So as mobile engineers, we've learned lots of stuff. We learned a lot about architecture, UI, UX, design patterns, testing, how to the release life cycle, you name it, lots of things. And so we could potentially apply all the stuff, right? But in which platform do we develop this? Okay, so I initially, like a couple of years ago, when I did this first circuit, I said, okay, I'm going to use this thing that Google made called Android Things. Let's see how it looks, right? And I made it work. It's a nice platform. It allows you to create like drivers in a high level thing and talk to the chips. What I wanted in an easy way, just applying the knowledge I have from Android development. But Google, being Google, got rid of that, and that's what happened with Android Things. So what do we do now? Well, we have things like the Raspberry Pi. Raspberry Pi is this little computer that lets you configure it, has lots of ports. You can install almost any Linux that you could imagine. You can basically, it's a Swiss Army knife, right? But what software do we put on it? So I was thinking we could do KMP, but if you have a look at the KMP documentation, you see server, Android, iOS, desktop, web. I cannot see embedded here. What do we do here? So I thought, okay, let's fix the documentation. So we could use actually the desktop target, using the JVM target for desktop. We could use that, and for the UI, we can use Compose multi-platform. That's no problem. It's we can render some nice UI. It works out of the box. With it uses Skia and Ski code. There's talks that go deeper into that. So no problem. Cool here. So I could create a UI, a simple UI using Compose like this that represents kind of the pedals, and it has some interaction when you press the buttons. That's cool. Not gonna get into much detail of how to do this because there's so many Compose talks out there and articles, so I don't think it was worth. But basically, it looks like something like this, and actually have the device here if you later want to. If you want to meet me later and we can play with it. I haven't brought the guitar or the effects. It will have been a bit difficult, but we can play with it a little bit. And yeah, that was it. But now we need to talk to the hardware. We need to do the next thing. Talking to that switcher, that ADG2188. So how do we do that? We have a look at the documentation of the Raspberry Pi, and also you can, that thing that we saw before, I2C, what is that? can we talk directly with that? And it turns out, if you see the documentation, that the ports, the pins that I use to talk to that I2C are these two, SDA and SDL, which is data and the clock. And if we put everything together, it will be something like this. We have the computer, the Raspberry Pi. We connect to the board that we made, and that connects to the jacks. And we connect the display by HDMI, or you could also use the ports to the side ports to connect some displays. But in my case, I used the HDMI. So what software we use for this? Is there any library, anything? Well, initially I tried to do it natively. There's a library to do, I see like GPIO stuff and natively for native target, but since desktop is a JVM target, I needed to do something that like a Java library. And this project is quite nice. It's very clean, very easy to use, and it comes with a Kotlin DSL. Like what can you expect? What is Sugar, right? So it's supposed to see that is the thing that we are interested in, as well as GPIO, because we might want to use that later for some of the stuff. So it's perfect. And just to go a bit deeper on this I2C protocol, it's just a protocol to talk to the chips. It's a big deal for the mobile engineers, because we normally don't do that kind of thing, but it's a standard. There's others like SPI or UART, but this is just a standard. And interesting about this protocol is that using just 2 pins, two wires, you can add a lot of target devices from one controller to many. And how does that work? And it works because each target device, each device that you want to control has an address that you either define or it is fixed in the device. So you can do up to 128, I believe, which is quite cool if you want to chain these things and do like more complex stuff. And if we keep going to the documentation, we still need to talk to this thing. And we see that you need to, every time you want to do the changes on this, you need to write 3 bytes. So one is the address, which the library deals with, the address of the device. There's a fixed part on this byte. And there's 3 variable ones that you can actually control by hardware. I just added a dim switch. Then the important bit that we need to build is the data byte, which is basically saying which input goes with each output and whether or not it's on or off. And then finally, there's a last byte, which just tells whether or not you are continuing writing commands. And this is necessary because you want to do everything at once, instantly. If you weren't doing like that, you will be changing one, then changing another. So with this byte, you tell whether you are continuing adding commands, and then the last one, it says, the last bit on that byte is the one that determines whether or not you continue. And if you finish, it's when that is added to the register and everything changes in the matrix, in the switcher. So let's see an example. So let's say we want to set on inputs 2 and output 4. X's are inputs and Y's are outputs. I don't know if I've mentioned. So first, on the first bit, we set it on or off. In this case, 1 on or off. Then in these 4 bits, it's just 2 in binary. This has 4 bits, and the other one has 3 bits, but it's because the table of truth has some kind of offset. But and then the last 3 bits is just for the output is 4 in binary, 1 0 0. No issues there, right? And how does it look to do this with this library? So very easy. We have a list of commands. We start the library like this. We configure our device. We say our device address that we have mentioned before. We add an ID, but that's optional, and then we use providers. This library is very flexible because it gives you the opportunity to use different providers. So you could access, and this means how does the access to the ports works below, at a low level. So this is using the Linux file system provider, but there's other ones. And it works fine. If you're familiarized with the Linux file system, it's just /dev, and then you have all the devices. That's how internally I think it's working. And then you write the commands, you iterate on it. And it's the cool thing with this DSL, it closes itself, so you don't need to handle anything else. You're done when you're doing that. And then I created this address byte for that command in the middle that we were talking before. It's just building what we said before. It's just doing some shifting of that one to enable of that bit to enable or disable the path, the address of the input and the address of the output. Just that, adding that offset that is particular to this the shenanigan of this chip. But yeah, that's very, very low level. No, but how does this translate into what we're doing? So we have these sets of pedals, these sounds that we were talking before, which is just a list of the pedals, and we convert them into a matrix. That's why I call the project the Matrix 8. And then what we have to do is, because this chip what keeps a state, we have to calculate the difference of the states. The current one and the new one. We diff the new one, and then we got the new diff state, and that gets related into the list of commands that we send. Like we are very efficient there. Imagine there's like a list, like a recycle view kind of thing with different things. You only update what you change, and there's lots of code here, but just to explain what this does, this basically translates the list of pedals into the array that we were saying. It's an array that 8x8 with ones and zeros, Boolean, true or false, and then finally we do the diffing and we get those bytes in the middle, and then it's sent to the command as we saw at the beginning. That's how we do the communication here with the chip. So I would like to do a companion app. So what communication can we use? Sorry. So we have several options. We can do TCP, IP-based stuff, right? Like Wi-Fi, WebSockets, MQTT, or we could use Bluetooth. So I think my first inclination was to use Bluetooth Low Energy, and that's what I used for the first iteration for several reasons. One of the reasons is it uses little battery in your device, and also on the in the thing that we are building, as well and as in the companion app, in the mobile that hosts the companion app. And it's very standard, very easy to work with. And the good thing about Bluetooth Low Energy is that you don't need to pair every time. You can just know in the identifiers of your service and your characteristics that we're going to see now. You can talk to it very quickly, in a nice way. But we could also use TCP IP-based stuff. So in the first iteration, as I say, I'm using low energy. Very problem it has is it has very low bandwidth, and you can only send a few little pieces of information, which is fine for the controlling. But then the next thing that I'm working on actually is adding something richer, like a REST service where we could just send a bit more complex data, and we can add metadata, and we could do a proper syncing of data between the companion app and the device. But let's start talking about the Bluetooth communication. So if you know anything about Bluetooth Low Energy, we can see that you might know that you need something called characteristics. Characteristics are like endpoints on REST. Let's say it's how you talk to from one device to another. It's the port that you use for that. And you can define many. And they can be read-only, read-write, get notified. For instance, we could, if you think about a heart rate monitor, that's a read-only device, read-only characteristic. But in our case, we're going to do read or write. As I say, you don't need to scan it. The companion app doesn't need to scan it every time and pair it with it. You can just, if you know the IDs, just say check if it's available or not. And for that, I found a library to be able to create the service. The library hasn't been updated in a while. It doesn't have the beautiful DSL that the Py4J has, but I'm very thankful that someone wrote that. And it gives you a simple interface to be able to create this Bluetooth service. And yeah, and it's useful. You can download it, and it's easy to modify. And this works if you have had a look at how to do stuff with the Raspberry Pi and Bluetooth Low Energy. You have a little bit of a problem at the beginning because there's no examples. Everything is Python, and it's amazing. But it's amazing the lack of the examples that we have for Java. But if you have a look at those Python scripts, you see that they're basically using the Bluetooth stack, which is the Bluetooth stack that you install in Linux. And it's BlueS provides all its functionality through the dbus, which is just a messaging-based framework, which has been there for ages. So basically, you could do the same thing with the Java application, which is what this library does. Sorry, too much code there, but just to focus on this is how you define a characteristic, and just to say this, a UUID, that's what defines our characteristic, and it has to be known by your companion app. And the path is the message that you pass to the Bluetooth stack. So it has to have a particular structure. And then you have to set it up, the characteristic. In our case, it's read, write, and notify. Both things. So we want to be able to read it from the companion app, to write to it, and to get notifications every time it changes. And then the final thing is just to get the listeners. So every time you add you write from the companion app, you want to be notified and react to that. And same thing when you write. Okay, writing the service, the code for the service is a little bit simpler. Again, the service has another UUID to identify it, and you have to configure the advertisement. I think I'm missing that code here, but you have optional things like if you want to have a listener to say every time a device connects, but that's optional. And then you need to start the service and stop the service, setting up your listeners. It's not that as beautiful as the other one, but it works. And then what I created for this particular thing, for the switcher, for the Matrix 8, was a super simple protocol. So on the R characteristic, you basically say the number of the pedal, whether or not it's on and off, and you change them. You can put as many as you want, and those are related to bytes. So very simple protocol. How does it look at globally? Now, basically, we have our normal structure of our app, the UI, presentation, use cases, and then the core of it is the switcher state. So we have like a state flow. Every time any of the, either from the UI, the I2C or the BLE changes that, the I2C gateway doesn't change it, but it's subscribed to it. But the BLE service or the UI can change that state, and then all the other ones and get all the changes. That's how I structured this app. So you change anything in the UI, the characteristic and the Bluetooth Low Energy gets updated. The I2C gateway talks to the chip. That's how it works. So that's basically it. But there are some things in work in progress. For instance, I didn't add the buttons. So for adding the buttons, we can use the GPIOs. The GPIOs are those general purpose pins. And if we go back to the layout slide, we've already used the GPIO 2 and 3 for the I2C. Sorry, I forgot to mention, GPIOs are pins that you can configure as input, outputs, digital or analog. So very, very configurable, very flexible thing. So we basically have all of those free to use. So the first thing is, how do we do the reading of a button? And again, we have components there, but there's basically two ways. It's either pull down or pull up resistor. This means that what are you considering to be pressed depends on the you could say, I'm going to consider high voltage to be my press state or ground. So in case of pull down, which is what I'm doing here, when it's not pressed, the state is high. It's 3.3 volts. It's a high voltage or high level, if you want. And when you press, it goes to 0. And that's when we detect that the button is pressed. And it's, again, using Pi4J, it's very easy to configure. Very, very easy. Sorry, going back. An example of 2 buttons I could do, but you could add as many as you want. And the important bit here is that you configure it as a digital input, and you say whether or not it's a pull-down resistor or a pull-up. In our case, in our diagram, it's a pull-down. You need to debounce it, because when you press a button, you think that it is going to take it easily with no problems, but there's a ripple. So it's not a square from going from 1 to 0. So you need to take that into account. You might have used the bounce on things like RX when people press, when you are detecting things like touch events. But this is the same thing here. You need to create something like smooth that pressing, and you don't have multiple presses. So. And then you react. In this case, as you can see, we are using a different provider, the Pi GPIO provider. Like before, we were using the file system. In this case, we are using the other one. And also, the other thing that we want to do is, when you select one effect, you want to know which one is selected. So we could add an LED. Same thing with the GPIOs. But this time, what we do is we set them as outputs. So now these pins are going to be outputs. And same kind of thing, you need the name of the number of the pin, and you set a state. Easy, no, there's no more here. So, done with haven't finished doing the buttons on this first iteration, but it's kind of the code is there, I just need to do a little bit of it. What is the next bit that I want to get done for this pedal? And it's configuring some HTTP, an HTTP service to do a kind of a more richer communication. But the thing is, when you are on a concert, you are in a gig, you might the signal of the Wi-Fi might be not very good, or you might not want to be configuring the device every time, entering on a tiny screen, lots of password every time, and also it's not reliable. So we could use something like Wi-Fi Direct, also known as Wi-Fi peer-to-peer. Basically, that device acts like the router, if you want, and you don't need to be connected to any network for this to work. Fortunately, there's nothing in like out of the box in Kotlin or Java. But I found this library very interesting. It has a Python script again, but. Yeah, I'm playing with it. I think I have kind of it configured. It comes with an Android app example, so kudos to this developer. And if you have a Python script, what you can do is, from your app, you can execute a command from the command line. That's what I'm doing at the moment. If anyone knows a better way of configuring the Wi-Fi Direct, configuring interfaces from Java or Kotlin or beautiful DSL, let me know. But at the moment, that's the way I found to do this. And from there, well, now you have that, you can define create your HTTP server. And we are in KMP, and the easy thing is just to use Ktor, right? Ktor is a nice library, and so sorry. Oh, sorry. Very nice library, and it lets you create a REST service very easily. You define the root, and you define your get endpoints, your port endpoints. If you wanted, you could do delete a specific pedal, whatever you want. You could use it for passing resources. Fine, easy. Yep. And that's what is work in progress. But I want to take this project a little bit further. I want to do the companion app. I would like to maybe, now that the project is in KMP, I could do a desktop app and a mobile app and share like 80% of the code. I want to do the edit mode where at the moment you just switch on and off of things and it's kind of hard-coded, but I would like to be able to do the drag and drop of pedals, and so you build your thing. Then the other thing I would like to add is a MIDI port, because we're talking about adding buttons, but what you could add a port and support the MIDI protocol. It's a protocol for music, for digital communication of audio equipment, if you're not familiarized with. And if you support the protocol, then it's up to the person that uses the device to say, okay, I need a super massive pedal controller with 20 buttons, or I need a tiny one with just two buttons. So that will be the benefits of it. And then there's all the things that I could do. Now that we have a computer there, why not just doing a little bit of processing of the sound? We could have a tuner that we could enable to tune the guitar and see it on a nice screen. We could do a little bit of signal processing, although the whole point of this is having your little analog pedals and being able to commute that. But you could do a little bit of it if you wanted. And then if this ever goes to production, if I get it further, I would like a better way of deploying and building a deploy. At the moment, I just have to go SSH into this device and update it manually. But well, I have a script, but it's very, very manual. So maybe in the future, getting to do something like that. And that's the end of the talk. Thank you very much for listening. You have the resources on the QR code if you want. That's the project, the sample project that has the code for the Matrix 8, plus all the libraries and documentation I've used for this. And thank you very much for attending. And also thank you for the people that have helped me with the slide, the people at Tesco in the UK, and my friend Matt Dolan that helped me a lot with going through everything. Yeah, that's it.